Hello.
All right.
Hello.
Yeah, I can start. Okay. Is there a
Morning,
question?
madam.
Good
Good
morning.
morning, madam. Is it
Is
clear
there a question?
video and audio?
I mean, you have to tell me whether I am clear in my video and audio.
Yeah. Yes, madam. It's clear.
Okay, fine. All right. So we go ahead.
Thank you.
So this is class 2.
Yes, madam.
Want the classroom to be projected? Yeah. Okay. So I have the VCAP classroom projected on screen. So guys, I'm watching you. Just quickly review what we did in the last class. It started with a simple circuit which had a voltage source and a resistor, and we started asking ourselves the question whether the lines, the conductors that connect the source to the load would make a difference to the circuit at all. And the key take home aspect is the following: yes, it would matter so long as your L over C would start mattering. Yeah. So we said it'll start mattering when when the ratio L over lambda becomes large, and we, as a thumb rule, we fixed a number 0.01, which is again an engineering thumb rule. Now the next question we asked ourselves is, how do we model this line? So turns out that what the line is doing to your signal is, at this moment we understand it as a delay. I apply a voltage at the source, and our understanding now is that it is appearing at the load after a certain instant of time. Now we start from what we know. We start from resistors, capacitors, inductors. So we know that capacitors and inductors in the circuit would start causing a delay. So we model this line as a bunch of capacitors and inductors. Now we need to place the capacitor and inductor in a smart way, such that even when you are applying a DC, the line should still work. So to say that I can't have the capacitor in series, or I can't have the inductor in parallel. Similarly, the inductor that we are putting in the model might not be an ideal inductor. It would have its own resistive component. Same to do with the capacitor. Its conductivity need not be 0. It could have a finite conductivity. So we choose this as the model. Now one of the questions somebody asked last time is, so we said this is our model for the line, but it does not matter relatively where you place your resistor and inductor. For example, I could have the resistor here, inductor here, and you could have the capacitor and conductance here, or I could have the resistance and inductance in series this way and then the capacitance. All this is actually a model for an infinitesimal length delta Z of the line. So the RLGC that we are talking about are the R's, L's, G's and C's of the line per unit length. Alright. Now in today's class, what we are going to do is go ahead with this model and see what happens. Can I find out how is the voltage evolving as a function of time, as a function of position? Similarly, how is the current evolving? from the concepts that we know. So we go back to the transmission line model. So we say a resistor, inductor in series, capacitor, conductance in parallel. And remember, we are modeling delta Z of the line. So if R is resistance per unit length, this value of the resistor is R delta Z, similarly L delta Z, C delta Z and G delta Z. Let us say the voltage that you apply, this could be at any section in the line. So the voltage that you apply is VZT input port, and at the output VZ, let's say this voltage is VZ plus delta Z at the same instant of time. So at the same instant of time, let's between A prime the voltage be V, and between B prime after the section of the length voltage is VZ plus delta Z. Similarly, let's say the current that is passing through this is IZT and the current that is coming out is IZ plus delta ZT. What's the objective now? The objective is to find VZ plus delta Z in terms of V. I want to know how different the voltage is when it passes through a section delta Z of the line. So how do I go about doing this? All what I do is to apply Kirchhoff's voltage law, find out how the voltages are related, and I would apply the Kirchhoff's current law to see how the currents are evolving. This is something very straightforward. If you have done circuit theory, you just keep calculating what is the voltage drop across each of these elements and write down the equations. So let's do that. I is a current through the resistor whose value is R delta Z. So the voltage drop across this, so I start from this, so I would write this as VZ plus ZT is the voltage across this. There is a drop here, drop in potential, so this would be minus resistance times the current. There is a drop in potential across the inductance, which is, we know from our basic definition of inductance, that is L di by dt. So I would write this as L inductance, but it's just not L, it's L delta Z. And when I write the differential, I have to be careful because the current is varying as a function of position, it's varying as a function of time. So when I do a differential, I want to be sure whether I am taking a differential with respect to Z, position, or with respect to time. So in this case, the voltage across the inductor is dependent on the rate of change of current with respect to time. So the derivative that I am talking about is del I by del T. All right. So that's the voltage here, and the voltage across this point B prime is the same as what is across a capacitor. So you would complete this equation, and that we have already said it is V Z plus delta Z T. And you have completed the circuit, so your right hand side is 0. So all what we did was to write Kirchhoff's voltage law for this simple loop. And what you're ending up is with, if I rearrange, I could write this as V Z plus Z T minus V Z T. I divide throughout by delta Z, and on the right hand side I have R I Z T. I have divided out the delta Z, so L delta I by delta T function of ZT. This is purely from Kirchhoff's law. I have not done anything special here. Now, in my theory of transmission line, I would like to model it such that I am trying to model the infinitesimally small length delta Z of the line, which means I wish to model this at a limit delta Z tends to 0. In the limit delta Z tends to 0. And we know from our basic understanding of calculus that in the limit delta Z tends to 0, this term sitting here is nothing but differential of V with respect to Z. And again, you have to be careful what differential are you talking about. This is differential with respect to Z here. So I would write this as partial differential del V by del Z. And I have a minus sign sitting here. So I have negative del V by del Z. That is equal to R, of course this is a function of ZT. R I ZT plus L. Remember here this turned out to be a partial differential with respect to T because we were talking about the voltage across Z. This is now ending up with, we are now ending up with a relation which tells you how voltage is changing as a function of Z across the line. How much is the slope of the voltage? What is the differential in voltage? Because we know from the basic idea of slope, if I know, let's say this is y as a function of x, some random function of x, if I know the value of the function at one point, how do I find the value of the function at the next point? If I know the slope, I can just do y is equal to mx and figure out delta y. I can say that delta y by delta x is my slope. So if I know the slope, I know what is the delta phi y for a given delta x. So essentially that is what we have figured out. Figured out how much is the differential change in voltage as we go across the line, and it turns out that that is depending on R and L and not on G and C, R and L, and on how fast is the current changing with respect to time. Alright. Okay, so we have this result. Now we go back and use Kirchhoff's current law here now. What would Kirchhoff's current law say? It's current branching law. You had I delta Z, so you apply it at this junction say C. So applying KCL, what do you get? You have I reaching this, and then you have a branch current into passing through C delta Z and passing through G delta Z. and you have I delta Z plus Z that is coming out of the branch. So you have current entering, you have a current leaving, and you have a current leaving. You apply all your sign convention and you follow whatever current entering as positive. I mean, be consistent with the sign convention that you use and write down this equation. The current entering is I ZT. Let me put current entering as plus. Current leaving is, you have current leaving through this, and if I have a capacitor, so the current leaving is, this is the capacitance C delta Z. I want to know what is the current through this. I know what is the voltage at this point. So I know that the voltage, if the voltage is V, the current is C dV by dt, right? So the capacitance is C delta Z. Again, partial differential V with respect to time. Now partial differential V with respect to time, I would write it as del V by del Z, del T, all right, minus the current through the conductance. Now remember, what is your conductance? Conductance is a reciprocal of the resistance. So if I just go by V equal to IR, I know that my conductance is 1 over R. So V times G is I. So the current through the conductance is simply voltage times the conductance. So the conductance here in this case is G delta Z, because the G in our notation is G per unit length. So it is G delta Z times the voltage. Now remember, what is this voltage? The voltage, is it V or is it V Z plus delta Z? We are talking about the voltage across this element, V across BB prime. So I should be putting this as Z plus delta Z T. Similarly, this would be Z plus delta Z T. So that is current leaving through this branch. We wrote the current leaving through this branch as sum of these two, and you also have the current leaving I Z plus delta Z circuit. So I can complete KCL with one I minus because this is current leaving. This is equal to 0. This is my second equation. So again, rearrange, I would get something like minus I Z plus delta Z T minus I Z T, divide throughout by delta Z, the same process that we did, is equal to, it is C del V by del T Z plus delta Z T plus G V Z plus delta Z T. Now again, go back and apply the same limit. In the limit, delta Z tends to 0. I know that this is the differential of I with respect to Z. So since I is a function of Z as well as T, I would write this as minus del I by del Z. And of course, as delta Z tends to 0, I can very well write this as del V ZT by del T plus G V ZT. So this is my second equation. So the first equation out here is telling me how the voltage is evolving as a function of position, and that is turning out to be dependent on the rate of change of current with respect to time. And interestingly enough, this equation is telling you how the current is evolving with respect to space, and that is dependent on how voltage is changing with respect to time. So what you ended up getting is two first order differential equations in space and time. Alright. Now historically this was first, these kind of equations were first formulated in maybe late 1850s or late close to 1900, and they used this. It's said that these equations were derived to explain why the telegraph services were poor across the Atlantic Ocean. So they were trying to figure out, they were trying to send Morse code from one side, Europe, to the US, and they were observing some delays, they were observing some issues. All they did was to connect lines, conducting lines, and they tried to now figure out what is happening to the voltage and current as you apply across the line. And so historically these were called, or these are called as telegrapher's equation. Alright, it's simply telling you if I have a time varying voltage, or if I have a time varying current because of a time varying voltage, then my voltage, there is a slope which is depending on the time variance. Now what do you do with these? This equation, okay, it's good enough to tell you, how the slope is evolving. But we would like to further know what is the voltage at each position on the transmission line. We want to know V as a function of ZT. Because if I have a line and if I have a source connected and I have a load connected, what I would like to know is at any given instant of time, what is the value of voltage across this. This equation is not telling you that. These two equations are just telling you how it is changing, what is the slope, right. So we want to get back one more step and we want to find out what is V as a function of ZT and I as a function of ZT. At any given instant of time, I should be able to find out what is the voltage or what is the current at a given position on the transmission line. Only then my problem gets solved completely. So, to be able to do that, we are going to do this for state sinusoidal wave, meaning the voltage that I have applied is of a fixed frequency omega, that is a sinusoid. In the steady state, there are no transients. In the steady state, it's a sinusoid, right? It's a single frequency. Now, question you want to ask yourself is, how far is this true for a real signal? Is this useful? But typically electrical engineers like to do this method because our Fourier theorem says that any periodic signal you can represent as the sum of sinusoids, and so long as your system is linear, the principle of superposition holds good, which means if I know the response for a frequency omega 1, I know the response for a frequency omega 2, then the response when I have both of them simultaneously present is simply the sum of the responses, right. So linearity is saving us, and because if it's linear, superposition will hold good. So I can analyze, or I can extend the analysis for any periodic signal. You know, if it's a square wave, it's a sum of, you know, many sinusoids with harmonics. So if I know what is the response of a single harmonic, I know what is the response for individually, I can simply sum it up. So this is a trick that electrical engineers usually play. Say that let me find out the response for one frequency, then I know how to figure out what will happen if I have multiple frequencies. Alright, let me deal with one frequency at a time. Now the reason why we are doing this is because mathematically it becomes much more easier, because I would write my voltage and current in phasor notation. In the phasor notation, just to remind you what the phasor, you would have come across phasor notation in your electric circuits course, but just to remind you, in the phasor notation I would write V, the voltage, as real part of the complex number Vz e power j omega t. In circuit theory you would not have seen this V as a function of Z, but because we are using transmission lines, we know that voltage is evolving as a function of position. So I should necessarily have V as a function of Z. In circuit theory you would have written this as V naught e power j omega t. This is what you would have written in circuit theory, right. So but here we are saying that there is no more a V naught, this V naught is actually changing as a function of Z. So let's figure out how it changes as a function of Z. Now remember, this part is time independent. You know, that's what the phasor representation does. It isolates the time dependent part from the time independent part. This is the time dependent part, and you have the frequency, angular frequency omega. And just to remind you, e power j omega t is the Euler's relation cos omega t plus j sin omega t. So you know, the real part of e power j omega t, just the e power j omega t is simply cos omega t. Now one more thing about this Vz is, it's time independent, which means there is no function of time coming there, but this could be complex in general. There is nothing that prevents it from being complex. It could have a real part, so my Vz could have you know, some real part, and you could have e power j5. Which college is this? This is VCAP. Can you please mute your mic? VCAP. Because I'm getting echoes back here. Thank you. So I was telling you that this could be in general a complex number. It could have a phase associated with that. But let's not worry about all that right now. We will figure out if there is a phase, it will come out from our analysis. So in general, there is no restriction that it is real. This could be complex. This is of course complex. E power j omega t is of course complex. And similarly, my current, I would represent in the phasor notation as Iz. I've been using small letter I, let me stick to that, e power j omega t. The way to do phasor analysis is, when you do the analysis, you would ignore this, you would not pick up the real part. You would say that the voltage is actually Vz e power j omega t, do the complete analysis, and in the end you say my actual voltages, look, it's real part of the complex number. That's the advantage of doing phasor analysis. So if I use these onto my telegrapher's equation, what is my telegrapher's first equation? Del z is Ri plus L di by dt, del I by del t. Now this del I by del t, if I go back and calculate, in the phasor, a derivative with respect to time is going to give me j omega Iz e power j omega. So that's the advantage of phasor notation. A derivative will now become a multiplier, right? And this is the reason why we went on to do this, because our analysis becomes simpler. So a derivative with respect to time, you can just replace it with a j omega. So you go back into your first equation, you will get it as minus, let me just write it explicitly for the voltage equation, Vz e power j omega t. The left side was the derivative with respect to space, right? So this is divided by z equal, the right side is Ri plus L del I by del t, Riz e power j omega t plus L del I by del t I could replace simply by j omega Iz e power j omega. And I know very well that this Vz is only a function of z now. So there is an e power j omega t is dependent only on time, it does not depend on z, which means this guy is a constant with respect to when you are trying to take a derivative with respect to z, and that e power j omega t is common throughout. So I could divide it out, because that is definitely not 0, so I could divide it out, and what I will end up getting is minus full derivative dv by dz. It became full derivative because now v is only a function of z. The way we have defined v and I is such that v is only a function of z, I is only a function of z. This could be complex, equal to R plus j omega L times Iz. So from the first telegrapher's equation, which had derivatives with respect to space and time, what we have done now is we have reached the station, but with only a derivative of space. There is no derivative of time here, because we used sinusoid, single harmonic, and use the notation. You do the same thing for the second telegrapher's equation, you will end up with minus di by dz. The terms are looking exactly the same, except that you see R I is replaced by G V and L del I by del T is replaced by C del V by del T. So I work out the same thing. This would come out as G plus J omega C V. Now these are the telegrapher's equation for the sinusoid. If I take the sinusoid in phasor form. Now again, this is not, we have not reached our objective. Our objective was to find V, Z, T. What we have ended up doing is, we have simplified our earlier equation and we have a differential equation which is now varying only as a function of first order differential equation which is varying only as a function of space. What does it mean? I know that at every position in the transmission line, I know how the voltage is evolving as a function of position. I know the slope of V as a function of Z. There is a small problem here. If I try to solve, these are actually coupled equations. Because when I am trying to solve for V, I should know the value of I, and if I want to know the value of I, sorry, this should be small I have been using small I here. So if I want to know what is the value of I need to know what is the value of V. So it's quite kind of tricky. If I want to know what is V, I should know I, and if I want to know I should know V. So there is a nice way of decoupling this equation. You want an independent equation for voltage and an independent equation for current, so that you can figure them out independently. And the way to decouple them is the following. You take one more differential of this equation, you differentiate this equation with respect to position. So what I will end up with, one more differential of dV by dz is minus d square V by dz square. R, J, omega L are constants with respect to space, so they come out as constants. Differential of I with respect to Z is di by dz, and quickly substitute this di by dz with respect to in terms of the right side here. So I will have R plus j omega L, G plus j omega C dz. I have now d square V by dz square, which is dependent only on V. I made it decoupled. Similarly, write down try and figure it out, what is the equation for I. Now in the theory of transmission lines, usually represent this constant, because all these are constants, you see. So you usually represent this as gamma square. So that you don't have to keep writing so many terms. There is one representation. This representation is useful in some other sense also, we will come to that. But my differential equation now reads d square V by dz square minus gamma square V equal to 0. Only functions of position. The contention is, if I solve this equation Vz, if I solve this differential equation, I will know what is the value of Vz. Once I know the value of Vz, I will go back and substitute it back in this phasor, and I find out what is the voltage and as a function of position and time. So that is the approach that we are going to follow. we will solve for Vz, and then you find Vzt as real part of Vz e power j omega. If I can do this for voltage, I can point and I will open the session to questions. But before we open, I will quickly summarize what we did today. We started with the resistor, capacitor, inductor, conductance model. We applied Kirchhoff's laws, voltage law and the current law. We ended up with the telegrapher's equation, but the telegrapher's equation we derived first is a little complicated in the sense that it had variations with respect to space and time. So to handle this, we introduced the phasor notation, and then we got two coupled equations, nice looking coupled equations, voltage in terms of current and current in terms of voltage, and we tried to decouple the equation, and now we have the final equation that we want to be solving to find out what is the voltage. Once I know the voltage as a function of position, I know what is the voltage as a function of position and time. So we will do the solution of this equation in the next class. Questions, please. Any questions? Please hand raise if you have questions. Well, if there are no questions, I will try to use up the remaining 10 minutes to solve the differential equation. Are there any questions? Please hand raise. All right, RVIT. Please go ahead with your question.
Good morning, ma'am.
Good morning.
Good morning, ma'am.
Good morning.
Ma'am, yes, ma'am. I want to know that why we are using phasor notation. It's quite typical to understand that why we are using it. So,
Okay.
we got all the
question
derivations,
is about
the phasor notation, why we are using it.
Okay. So let me repeat the question. Why are we using the phasor notation? It looks very complicated. And
Yes,
the answer is the phasor notation is used to simplify, not to complicate. Okay. So
just to
you
simplify
see,
this,
when I write,
actually, ma'am, I want to say that it's quite typical to understand that why we are using it. It means it's simple, but to remove the time, it's not understandable that from my side.
you see, the basic logic is the following. These
Yes.
voltages are the voltages or any signal for that matter. If you know that its variation is in time, is going to be of a very well defined frequency, right? You know that it's going to change in a very well defined way, which is given by its angular frequency, or from your Hertz frequency you convert to angular frequency. Then I don't have to worry about solving that. You know that variation, right?
Yes.
You don't have to worry about carrying forward that variation, because you know very well that it's going to change. If it's 50 hertz, it's going to keep doing 50 hertz as a function of time. So that part is included in your e power j omega t, right? And
Yes.
what we want to worry is, we want to focus our attention on what we do not know. which is evolution of voltage as a function of space. So here the reason why we are using phasor notation is to say that look, we know how it's going to change as a function of time. That's not going to change in the transmission line because it's a linear system. If I've excited the system with a frequency omega, the system is going to respond with a frequency omega and none other than omega, right? So then time derivatives become very redundant, you know, time derivatives become just j omega multipliers. So that is the reason why we are using phasor notation. Now you could also think about, you know, why would you need this imaginary part? Right? So as a notation you would use this as e power omega t to complete the phasor, because the phasor would be, you would have learned X number class that it would have a real part and it would have an imaginary part, right? And the component of this complex number along the real axis is the real part and the angle it makes is your imaginary part. So in that representation, as time is progressing, your omega t is changing, which means your phasor is rotating in the complex plane. Associate a phasor, a physical representation of the phasor in the complex plane. So if I have, for example, e power minus j omega t, it would mean that the phasor is doing a counterclockwise direction rotation, right? So you can think about, you can associate this with your complex number understanding also. All right.
Thank you. Thank you, ma'am.
Yeah. Any other questions? Please hand raise if you have questions. Any other questions? If we don't have, then I'll use the next 5 minutes for continuing the class. So I go back to my whiteboard and talk about this gamma square a bit before we solve. So your gamma square is this guy. So gamma is under root r plus j omega L j omega C. This is a complex number. This is a complex number. So the product is a complex number. Square root of the complex number is a complex number, which means gamma is complex in general. I could write this gamma as, say, alpha plus j beta, because I calculate all the complex numbers. For a given transmission line, you would have a certain resistance, certain inductance, certain capacitance, certain conductance for a certain frequency. I can write all that complex number, represent it as a real plus j imaginary part, and alpha and beta are now dependent on not only R, L, G, C. What I want to highlight is it's dependent on omega, which means this constant is going to change with frequency, with the frequency that you are using. Different frequencies would respond differently, right? Now we go back to the solution of this equation, second order differential equation as a function of space, and maybe as a homework I want to try out this solution. V naught I call this as plus V naught plus e power minus gamma z plus V naught minus e power plus gamma z. The homework for you is to substitute so this is my assumed solution. I am proposing a solution, substitute Vz in the second order differential equation and find out whether it satisfies the equation. Right. So I leave this as a homework to you to go back, substitute this, go ahead and substitute this. In fact, you would realize that even if I just take one term, it might still satisfy. Just check whether you can satisfy this equation with one term, whether you need the second term or you need a linear combination of these two terms to satisfy this differential equation. Once we have figured if it's satisfying, then we can go ahead and assume that this is the solution. So the homework is to prove for yourself whether the suggested solution is satisfying the differential equation, and then we can go ahead and see why I put this plus and minus. Do not worry about that right now. Plus and a minus here, we will figure out what is the physical interpretation of that. That we will do in the next class on Tuesday. Any other questions? Please hand raise. Please hand raise if you have any questions. All right, if there are no questions, we stop the class here and come back on next Tuesday. Thank you.